IoT Unplugged. Tune in to the Internet of Things. Micro-electromechanical systems, or MEMS, timing devices represent a significant advancement in the precision and reliability of timing solutions, especially crucial for the burgeoning fields of IoT deployments, 5G, and edge computing. These tiny yet powerful components provide unparalleled accuracy in timing, essential for things like the synchronization of data transfers, enhancing network reliability, and device performance across the IoT ecosystem. With the advent of 5G and the proliferation of edge computing, the demand for high-speed, real-time data processing and transmission has never been greater. MEMS timing devices, with their reduced size, lower power consumption, and superior resistance to environmental variables, enable IoT devices to operate more efficiently, maintain consistency in connectivity, and support the rapid scaling of networks. So how will MEMS timing devices adapt to the future technological challenges and opportunities presented by the next wave of innovation in IoT, 5G, and edge landscapes? To discuss this further, I'm joined by Piyush Sevalia, Executive Vice President and Marketing of SiTime. Piyush, thanks for joining us today. Could you start by introducing yourself and sharing a bit about what SiTime does?
Sure. Hey, thanks for having me on and great to be here. My name's Piyush Sevalia. I'm the EVP of Marketing at SiTime. And what SiTime does actually is we're transforming this world of timing devices. It's a category that you may have never heard of, but it's super, super critical to all electronics today. Timing is the heartbeat of electronics. And so, what it does is it puts out the clock signals that make electronics work, whether it is a processor, whether it is memory, whether it is high speed serial circuits like Ethernet and things like that. Everything runs on timing. And this has been an industry that's been around for the last 80, 90 years. What we are doing is operating in a category called precision timing, which is much more accurate and stable under all conditions, whether it is shock, whether it's vibration, whether it's power supply noise, things like that. And that's what we do. And we use a very unique technology called MEMS, micro electromechanical systems, uh, to create our timing devices. We are the leader in the space. We have over 85-90% market share. And we are shipping to pretty much all the important customers in time in electronics that you may have heard of. So that's what we do. We've been around for since 2005. We're a publicly traded company on the Nasdaq, and basically we have really started transforming the world of timing by giving customers unique benefits and solving their problems as the whole world of electronics moves into this, intelligent, connected world with a lot of AI, with a lot of processing and things like that. That's where we really solve some pretty fundamental problems for our customers. So that's who SiTime is. I've been here for 16 years. My responsibility is about basically helping grow the revenue, helping grow the product roadmap, and all the things that go along with that, as well as, of course, external communications.
Okay, great. Well, leading us off nicely into our first question. So, talking about MEMS, how do MEMS timing devices enhance the reliability and efficiency of IoT devices, especially compared to traditional timing solutions?
So, good question. We think of IoT devices in two categories. One category is the clients that we hear about a lot, the sensors that are placed on highways or in buildings and things like that. We even consider wearables as part of the IoT devices, the client base, and then the IoT infrastructure side. So that's two. You could also look at it from another way, which is consumer IoT and industrial IoT. So, but the first categorization, infrastructure versus client. One of the things that we do in IoT devices, first of all, the client devices, IoT devices, are going to be pretty small. They're going to need long battery life because they're going to operate out in the world for a long time. And this is where our MEMS timing devices actually help quite a bit. So when we think of an IoT client device, it's small, it's low power, it's connected, but the connections are not going to be typically always on because that's going to drain your power. So you have to have connections that will come on and go off. And in all of these categories, I think MEMS timing devices do beautifully. First of all, MEMS timing devices are small. Um, our our MEMS resonator, which we use inside our oscillators, resonator is just a mechanical vibrating element. Oscillator is actually a device that generates a clock. Our MEMS resonators are tiny. It's zero point 0.5 by zero point 0.5 millimeters in size. The smallest quartz resonator, which is the legacy technology that's been around for a while, the smallest quartz resonator is 4 times that size. So we give the customers, with our MEMS technology, we can give customers the benefit of smaller size. That's one. Another place where we can help is in power consumption. So all of these IoT clients will typically have a timekeeping device, which will basically be always on, and it will just keep track of time, and it will tell the radio interface when to come on and when to go off. Now, as you can imagine, the radio that's consuming the bulk of the power in these devices, uh, if it comes on and stays on for a very long time, then then basically you're going to consume a lot of power. So you have to be very precise in turning that signal on and then turning it off. Now, our MEMS timing devices, um, we measure the stability or accuracy of this device, meaning how close is it to its ideal clock signal. We measure that in parts per million. And so our devices, in the size that we offer, 1.2 millimeter square device, can go as low as 3 parts per million stability. First of all, the quartz devices don't even get anywhere close to that. And second, their stability is going to be of the order of 200 ppm, so almost 60 times worse. Now, this stability allows us to turn on and off the timekeeping devices much more precisely. I'm sorry, the radio frequency, the radios in these devices much more precisely. And that allows us to save power at the system level. So that's the second benefit. The third benefit is in what we call resilience. The device, in a timing device, whether it is MEMS or quartz, because there is a mechanical vibrating element, it can be impacted by environmental stressors like shock or vibration or temperature changes. And in our devices, our MEMS device, because it is so small, it is more immune to shock and vibration. I mean, if you think about the old physics law, force is equal to mass times acceleration. The lower the mass and the same amount of acceleration, the lower the force that is going to couple on it. So that's why our devices are 30 to 40 times more immune to shock and vibration than quartz devices. So now you take our devices and you put them in, for example, a highway, on an IoT client on a highway, a sensor that is measuring the load on a highway or something like that. Or for that matter, so you have a device that is in a buoy which is sitting in the middle of the ocean somewhere. And in these kind of applications, you're going to be subject to constant vibration. And our devices are much more immune to that. So we enhance the reliability of the end IoT device by when the customer uses our devices for timing. So that's a third way we help people. So on the client side, size, power, reliability, in that order. If you go on the infrastructure side, Uh, Maybe power is not as important, but the environmental resilience and reliability is a lot more important. And so that may come first. Second may be size, and third may be power consumption. So it depends on where the application, the end application is, where the end device is used, and therefore the trade-offs that come along with that. Now, whether it is on the infrastructure side or on the client side, there's a uniform benefit that we offer to customers. Our MEMS devices are made from silicon. So literally, I mean, if you think about it, if you have a wafer, which is we typically use 8-inch wafers for our MEMS. But you have an 8-inch wafer, you have anywhere between 60,000 and 120,000 MEMS die on there. And each one of these die is vacuum sealed. And so literally what ends up happening, and the reason why you want it to be vacuum sealed is because you want to the MEMS resonator to vibrate with without any external resistance such as air. So you operate it in a vacuum. Quartz devices, what they do is they actually cut a piece of quartz crystal, put it inside a ceramic package, and then vacuum seal the package. And that fundamental difference, where a MEMS device is sealed at the silicon die level versus a quartz device is sealed at the package level, gives us much better reliability. We are typically semiconductor level reliability. You're talking a billion, 2 billion hours MTBF, versus a quartz device is typically of the order of 50 to 60 million hours MTBF. And so in that case, our reliability is much higher. Now, you may say, millions of hours of MTBF, what does that matter anyway? But fact of the matter is, MTBF and reliability is a statistical calculation, and these things start having impact. So that's a fundamental benefit, better reliability, semiconductor level reliability that we offer to pretty much all our customers. So that's how we are improving the benefits and the features of the end IoT devices in which we are used.
Okay, well, excellent. Well, you've given us a good rundown of how they help enhance reliability of IT devices. I was wondering, what about how do MEMS timing devices help in the context of emerging technologies such as 5G networks or edge computing? And, how do you anticipate the integration of these timing devices in these IT deployments involving them?
Great question. We've actually seen quite a few of our customers going into those kind of applications, 5G infrastructure, of course, 5G client, but we focus more on the infrastructure side. And we've also seen usage in edge computing devices. I mean, data centers is pretty, it's on everybody's radar these days. And in data centers, for example, you have a server, you have a top of the rack switch, you have leaf and spine switches, you have smart NIC cards, network interface cards, and you also have acceleration cards for doing AI processing. And we are used in every one of those applications. And again, the core benefits remain the same. However, so for example, one of the core benefits could be environmental resilience. I talked about that. Maybe here, the shock and vibration piece is not as important as power supply noise rejection, because power supply noise rejection is, I mean, you will always have power noise on the power supply lines, and that noise can have pretty bad effects on the performance of the timing device. So the more immune you are to this power supply noise, the better off you are. And our devices, we design them in such a way that we offer much better immunity than our competitors' devices. So that's one benefit. Another benefit is temperature changes. You can imagine, because these are processing some pretty heavy data. I mean, large language models, for example, where you are like training the system on all this data that you're feeding it, and in those kind of applications, the temperature change inside the system can be very rapid. You're talking, I mean, we're talking anywhere from a couple of degrees centigrade per minute up to a few degrees centigrade, 3, 4, 5 degrees centigrade per second. And in these kind of very rapid temperature changes, again, the timing device has to be more immune. It has to be immune to these because if it's not, the frequency of operation can change and that can mess up the whole system. And we're happy to say that our MEMS devices offer this what we call DFDT. It's a rate of change of frequency with temperature. Our devices are at least an order of magnitude better than many of the quartz devices out there. So, as I said, while the specific environmental parameters will change when you deploy devices in edge computing, for example, the overall benefit is still environmental resilience, but the specific benefits are more immunity to temperature changes as well as more immunity to power supply noise. Vibration and shock play a lower role. You go into 5G networks, vibration and shock play an important role, along with power supply noise and temperature immunity. Think about a typical 5G network. You're trying to pump 10 times the bandwidth of 4G into the system. And for that to happen, the timing has to be 10 times better. That's just defined in the standards. Now, for you to be able to deliver that kind of bandwidth, your 5G radios will have to be mounted in non-pristine environments. So whereas a 4G radio would have been mounted in a slightly more pristine environment, since this is getting closer to the customer, you got to mount it in a non-pristine environment. I mean, we've seen deployment happening on the side of stadium walls. We've seen deployment on traffic lights. We've seen deployment on electricity poles, the transmission poles, and things like that. And these things are placed next to highways, next to railway tracks, and things like that. So when a large freight train goes by, when a large truck goes by, those poles are going to be vibrating. And when they start vibrating, that impacts the timing device in there. That can cause basically calls to drop. And so that's one of the benefits that we offer in those kind of applications, that we are very immune to these kind of low frequency vibrations that you're going to see in outdoor 5G deployment. And when you have a baseline spec that says your timing has to be 10x better than 4G, and then you have to be immune to all these environmental stressors that are out there, we think we are the best device out there. And many of our customers think so because they're using us. We've been deployed in quite a few 5G radios that have been deployed out there, and we continue to be in that space. So ultimately, if you look at it, at the heart of all of this, better environmental resilience, better reliability, smaller size, lower power, those are the four core benefits that we offer. But depending on the application, one takes priority over the other.
Okay. Well, you mentioned why the MEMS timing device you believe has superior qualities over the quartz products. You've been giving examples, but I was wondering, could you provide real-world IoT applications in which you think this is applicable, in addition to the networks that you talked about?
Yeah, so one of some of the applications that we've seen, seismic sensors. You put these sensors underground, and for a variety of reasons, whether you're measuring or whether you have an earthquake measurement network so that you can provide early warning signals, or whether you have what do you call it? You do oil exploration, for example, and you need these sensors down under the ground. Those are the kinds of applications where these sensors are used. We are in those. We are in ocean sensors, where you are sitting on a buoy on top of the ocean in the middle of nowhere, and you have to transmit signals through satellites. That's one example, and you could be measuring tsunamis, you could be measuring just other environmental conditions out there. Uh, we are in un, we are in devices which sit on the floor of the ocean, especially in areas like Japan, where the tsunami threat and the earthquake threat is very, very real, as we've seen before recently in the last 10, 15 years. Coming back more to terrestrial areas, we're getting starting to get used in quite a bit of factory automation equipment, whether that's connectivity, whether that's computing, whether it is just a variety of different things in factories. I mean, even robots in factories were being used in that. And I know I'm using the word IoT quite loosely here, but I think the industry does actually consider at least some people in the industry consider this to be part of IoT, industrial IoT. So we're seeing examples there. Um, what else can I talk about? On the consumer and client side, sensing networks in buildings, in highway equipment, I mean highways, things like that. We are being used in those kind of applications. Purely on the consumer side, we've been in wearables for over a decade now. Um, what else? I mean, if you expand beyond IoT to automotive, for example, in cars, I mean, bunch of electronics going in cars. Oh yeah, the other one is cameras. Uh, Basically, when you deploy cameras, security cameras for your home, for your office, and things like that, we're in a lot of those applications. So yeah, these are many of the applications. I think totally we have about at least 320 applications that we've identified so far, and they're growing every year. But we've identified about 325 applications so far that we are in. So it's a very broad market. The use case is tremendous. There's just a lot of places we can be used.
Okay, great. Well, talking about its use, I was wondering how could it play a role in enabling synchronization of various IoT devices within a network, especially in large-scale deployments?
Great question. So let's go back to the fundamental need for synchronization. As you're going to transmit more data, if your networks are synchronized, if the device is synchronized to the network, then both sides know exactly what the time is. And because both sides know exactly what the time is, you can transmit data a lot faster. So the benefit synchronization is actually getting much more popular today as the speed of networks increases. Synchronization is done through something, a standard called IEEE 1588. And there are various levels of accuracy of synchronization that you can provide. For example, in a 4G network, all the nodes in a 4G network from end to end have to be time aware and 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 within 1.6 microseconds of accuracy to each other. In a 5G network, that accuracy, the node to node accuracy, goes to 130 nanoseconds. So obviously, not only does the baseline timing device have to be better, more stable, and less susceptible to environmental stressors, because the more susceptible you are, you're going to blow through that time error budget pretty quickly. So that's one place, and then the other thing is the kind of protocol that you use for synchronization. I mean, yes, the overlaying standard is 1588. But underneath that, you could use something called PTP, which is Precision Time Protocol, or NTP, which is Network Time Protocol. You can even synchronize your networks to actually, as part of all of the synchronization, you have to have a baseline signal that's coming in from the GPS satellite, because that basically is your core time signal that you're going to get into any of these synchronization devices. So on the infrastructure side, typically you will have a system that uses an ultra-stable device such as a TCXO, a temperature compensated oscillator, or an OCXO, an oven-controlled oscillator. And these are just highly stable devices. For example, an OCXO has a frequency stability of 1 part per billion over a temperature range of minus 40 to plus 85 degrees C. So it's highly, highly stable. And in a network, when you deploy an OCXO to provide something called holdover in synchronization. So when the network clock disappears, whether it's coming from a GPS or it's coming from a grandmaster somewhere in the network, and that clock disappears, you basically automatically switch over to the local OCXO. And what that will do is it will provide the time accuracy in the network so that all the downstream nodes continue to remain synchronized and the data transmission continues to occur. So that's how one of the ways in which we are helping synchronization on the infrastructure side. In terms of the client side, like IoT devices, sensors, and all that, um, the way those one of the examples where we've seen it's not real time synchronized, though that is getting more popular. So we've yet to see 1588 protocols running on some of these, for example, buoys that are sitting in the middle of the ocean. But there we play a different role. These devices are there without network connectivity for a long period of time. And in some cases, the GPS signal may not even be there. So the timing device that is used in these clients has to be so accurate that when the device wakes up and is ready to transmit data, it can easily lock to the GPS signal, and for that to happen, your time error on the client device has to be very, very tight so that you can wake up and lock to a GPS signal quickly. And that's something that we provide. So we basically provide the capability for these devices to have a very accurate clock so that they don't have to keep on waking up and locking to the GPS signal. They can stay in standby mode for a longer time and therefore preserve battery life. So these are the ways in which we help synchronization of the networks.
Okay, great. You mentioned stability being a key aspect there. I was wondering about external environmental factors such as temperature, vibration, and electromagnetic interference. How does this affect the performance of the MEMS timing device in IoT deployments?
Typically, we are so. For example, you look at vibration. We're anywhere from 10 to like 1,000 times better than quartz devices in terms of immunity to vibration, in terms of immunity to temperature changes. Again, 10 to 40 times better. Um, if you look at electromagnetic interference, now that's an interesting one. We saw a few cases of that a long time ago, but we've pretty much designed our devices to be pretty immune to that. So let me give you an example. One example is when your device, timing device, is sitting in a network dense area. You have multiple radio RF networks that are in that part of the electronics, whether it's like Bluetooth or Wi-Fi or NFC or radar or lidar or whatever it is. I mean, so because you have a bunch of these RF radio networks around you, you could see a fair amount of EMI coming into the device. And so you have to obviously be immune to that. A very long time ago, we started seeing examples of this. So we actually paid a lot of attention to that during our design, the analog design part phase of the project. And so way back in 2009 or 10, we just boosted the immunity of our devices to EMI dramatically. And that helped us actually. So we haven't seen any issues or explicit examples of customers running into these kind of issues recently. But a long time ago we did, and obviously we basically made our devices immune to that. There's another part of EMI that kind of comes into play too, which is the amount of EMI that your timing device puts out into the network and that is for basically electromagnetic compliance, whether it is FCC Class A or B in the US, or in the Europe has its own EU designations. Your device has to be below a certain level of emissions, not just at the base frequency, but at the harmonics of that frequency too. And and a variety of electronic devices, a variety of ICs inside the system can cause problems with compliance, EMC compliance. So one of the things that we do, we actually offer two very specific features on our device. One feature is to basically control the slew rate of the outputs. So you can turn on and off the outputs a little bit slower. And what that does is that it reduces the basically the emissions of the harmonics of the base frequency. So that's one way we can help our customers control the EMI that is going out from their electronic device into the environment. So that's one. The second thing we do, we actually on some of our devices we offer something called spread spectrum. Spread spectrum is a technique that has been used to reduce EMI for the last 3 decades. And what it does is it actually goes counter to what we've been talking about, which is very tight stability. In this case, you're actually introducing the frequency has to be spread around, so the ppm increases. And of course, you can only use it in places that can tolerate it, like microprocessor clocking. You can't use it in high speed serial networks like Ethernet or things like that. But this spread spectrum clocking also allows you to spread the energy of that clock. Instead of it being a very sharp peak in the frequency domain, it actually becomes a more like a hill with a slope, a gently sloping upslope and a gently sloping downslope. And what that allows you to do is spread the energy so that you're not emitting that much into the environment. So we offer designers techniques on how to reduce the EMI that is coming out from their electronic device. So there's that too that you have to take into consideration. So as I said right at the beginning, right? I mean, we are here to solve problems for our customers. And so we have a variety of these kind of features built into our devices to help customers basically solve their timing problems, whatever they might be.
Okay, right. Moving on, I wanted to know what your belief is the growth of MEMS timing devices in the IoT ecosystem. What is fueling that, and how is the market responding to these trends?
So, without getting into specifics, at the high level, what we see, obviously, adoption has been great. We are now cumulatively over the last decade or so, we've shipped to decade and a half. We've shipped to a total of, I think, 15,000 customers. Um, Small, large, medium size, worldwide. I mean, literally, pretty much all around the world. Uh, we actually see a pretty good adoption rate in the industry for our MEMS timing devices because of the value that we deliver to customers. And so we saw a pretty rapid growth happening from, say, 2019 all the way to 2023. 2023 was a year of inventory consolidation just because of the shortages. There was some excess buying that had happened, and people were consolidating their inventory last year. And we basically talked to the financial analysts and the industry people out there, and we expect to see pretty good growth going forward. The overall industry is typically growing at a 4 or 5% rate. Our target growth rate is north of 30%. And so anyway, so yeah, that's where we are. Ultimately, look, the product's gonna talk. And if you design a better product that helps solve customer problems, then that will get traction, and that's what we are seeing across all of our devices.
Okay, I'm talking about your products. I was wondering if you could share insight into the future developments in MEMS technology that you believe will, continue the application of MEMS timing devices in IoT applications.
Yeah, so again, here I can't get very specific because I can't talk about the roadmap specifically, but that at the higher level, the problems we are trying to solve, basically at the system level, if you think about it, people want higher speed in the networks, people want more processing power in their computing environments. and people want lower power consumption, and people want smaller size, and people want more immunity to environmental factors. And so we basically target those five key factors because different people have different weightage on which one of those is more important to them. And so that's what we focus on. So we'll come out with a bunch of different devices. I mean, our OCXOs, for example, are completely focused on environmental resilience and infrastructure networks. Our what we call our low power timekeeping devices, our 32 kilohertz devices, they're completely focused on size and power consumption, as well as, of course, reliability and environmental resilience that we offer. But it's more important for our customers to get it smaller and make sure that the system is lower power there. So depending on, I mean, we have a very broad roadmap. What we do is, actually, maybe this is the right time to get into some of the product areas. Um, if you think about it in timing, there are three different categories of products. One is resonators, mechanical vibrating elements. They need a circuit to create a clock signal. One is oscillators, the mechanical resonators coupled with a circuit, all inside the same package to put out a single clock. And then the third is clock generators and buffers and network synchronizers. Those three categories of devices, they put out multiple clocks from the same device. Until today, about 90 to 95% of our revenue has come from oscillators. That's been our focus. In 2020, we actually introduced our first clock system on a chip. We call it the Cascade family, and that's a family of network synchronizers and jitter cleaners. Uh, we call it a clock system on a chip because we've integrated the MEMS resonator inside, versus until then, most of the devices that you saw being offered had a quartz resonator or a MEMS resonator outside. By integrating the MEMS resonator inside, we make it a complete timing system. The customer does not have to deal with the noise issues that come from the traces from the resonator to the clock device. The customer does not have to tune one for the other. All those problems go away. They end up saving 2 to 3 weeks in design time because of something like a Cascade device, which has the MEMS integrated inside. So that's something that we are expanding into. Last November, we also acquired the products from a company called Aura Semiconductor, which is based out of India, and we've got all those products that we are offering to our customers now too, and starting to get design wins there. And then to talk a little bit more about the resonators, while every one of our devices uses a resonator inside, we have yet to offer a standalone resonator that the customers can use in the system. So, yes, it is part of the roadmap in the future, but not right now. So, from a roadmap point of view, we expect to see in the IoT applications, we expect to see a lot of oscillator usage, maybe some low power clock usage for the applications that require multiple clocks, and finally resonator usage too.
Okay, excellent. Well, I think that's a good place to end it. Piyush, thanks for taking the time to speak to us today.
Thank you for having me on, and thanks once again.
IoT Unplugged. Tune in to the Internet of Things.